My name is Sundar Shrestha. I would like to first acknowledge my co-author, my supervisors, Dr. Qing and Professor Maksym. As Chairman already mentioned, I am from Center for Railway Engineering in Central Queensland University, Australia. So, welcome on board. And I will take you through a 15-minute journey of this presentation. And in this journey, I will cover about our project, overview and approach of adhesion estimation. A contact model is proposed to estimate adhesion that will be discussed. It will be validated through BOGIE test rig, which is developed in Genesis. And it will be validated through 3 different case studies. And I will outline future works in the end. Okay, so this should be something. Okay, so this is my status of project. The main aim of this project is to estimate adhesion condition between wheels and rails. And it has anticipated 6 stages among them. First 2 stages are already completed, and today's work will be based on these two stages. And we are from heavy haul background, so for your interest. I think I don't have to tell you much about why adhesion study is required among us. So you know why, because if we have proper information about adhesion condition, then our railway system will be efficient, more productive. It will be cost benefit as well. And that's why we are into this innovation. So let's talk about adhesion estimation. So at the beginning of this project, we had an extensive analytical review on adhesion estimation. It has been already published. I think it's not that clear, so if you cannot see it, you can go online. It suggested that for adhesion estimation, we need 3 special things. That is system input, purpose of adhesion estimation, and response time. So these 3 are main factors which can change the game. And it also suggested that all those approaches have been verified under normal running condition, meaning it will be different. The result will be different under traction and braking. So in our project, we have applied adhesion estimation approach in modular approach. So first of all, so adhesion condition will be determined from adhesion condition detection algorithm, which will be discussed next slide. Once we have adhesion condition, and that information will be used to determine actual adhesion coefficient. And for that, we have proposed a special contact model which produce slip and creep process information, which also will be discussed in detail in later. So let's jump into the adhesion condition detection algorithm in very simplified way. I'll try to make it very simple so that everyone can, one of us will understand it. So first of all, let's go back. Adhesion coefficient is estimated from braking or traction force and vertical force. So we'll have a curve dependent on velocity and slip. So this one is for dry condition. Let's say the current velocity is 20 kilometers per hour, and this is for dry. So there is another 2 more low, and then wet condition curves as well. So when it's like just for 20 kilometers per hour, then it comes to a very simplified curves like this, which is only dependent on slip. So let's consider the slip 0.1. Then there are 3 probable adhesion coefficient, which are 0.2, 0.25, or 0.3. So from those information, using minimum absolute difference, we can find the condition. Yeah, in this case, the minimum difference is 0.2 minus 0.2, which is low. So it will return low, 3. So this algorithm will return 3. So after having this information, let's jump into the proposed contact model. Oh, yeah, it's working. So it is modular based. It has 5 modules. The first module is profile generator, which is only concentrated on the region of interest, which is between, some specific profile between wheels and rail. And there is a module called Creepers module, which offers sleep. There is 10Z contact module based on Pollack. So it's algorithm which produces creep force. And for normal contact problem, we have used theory of force and approximation function reported by and Salat. And there is geometrical model which consider multi-point, which will be described in next slide. So the main purpose of geometrical model is to determine the contact point and its corresponding curvature, contact angle, and other related information. So it has 2 main sections. One is finding the contact point, and second, to determine whether the potential contact points are exact or not. So let's jump into this section. So first of all, the penetrated profile is determined from the region of interest, where you can see the penetrated profile dz, which also delta z here, delta z. Then extreme points such as CP and EF are determined. And for multi-point, so if it is just single point, then CP1 will be determined. But if there are multi-point, then this might be the scenario. So in that case, if it is multi-point, then extreme points such as E and F will be there. So that is one of the requirement. And there is also requirement of width between 2 points. So once we have potential contact points such as CPs, then it finds whether those potential contact points are correct or not from the penetration requirement. That's how the contact points are determined. So we have contact condition, we have contact model. So to input the state vectors to the contact model, we have, and also to validate, we have designed on BOGIE test rig based on reference 2, which has 1 car body, 1 bolster, 2 side frame, 2 wheel set, and 2 roller set in Genesis, as you can see on the right one. And its corresponding force mass constraint with a number of degree of freedom on the left. So we have almost everything. We have done so many things. Now it's time to validate setup. So we did 3 simulations. The first one is to validate the proposed contact model. And second and third is to detect adhesion in constant speed and braking mode. To validate our contact model, we did against Genesis KPF, which stands for contact point function. And we also consider the same wheel road profile. And we have done several parametric validation, and among them, one is presented here, which is contact ellipse semi-axis ratio. We can see the result is a little bit different here at the contact switch and in flange area, because at that stage in that proposed contact model, yaw angle was not considered. To detect adhesion condition, in constant speed, 20 km per hour was selected, and the longitudinal slip was adjusted in order of dry, low, wet, that is 1, 3, and 2. And you can see the corresponding adhesion coefficient, longitudinal creepage force, and then detected condition 1, 3, and 2. Similarly, in braking mode, the setup was for first 30-second wet condition was adjusted, and then low condition, and then dry condition was adjusted for remaining until it stops. And you can see the result. It was perfectly detected, wet, low, and dry. So from all these experiment, validation, and study, it can be concluded that algorithm is operational because it can handle slip under variations of adhesion condition, and the result is anticipated in both rolling and braking conditions. So we already started to experimental validation work in our test rig, which is available in our research center. And all those output and all those information will be provided in next presentation, hopefully soon in future. So please stay tuned with our project. So I would like to acknowledge Rail Manufacturing CRC for fund and through project R1.7.1. Thank you so much. So please let me answer one or two questions.